Hey, welcome back. Today we're going to be covering Newton's third law. Newton's third law is really interesting, and it actually leads to some pretty funny situations if you don't know what's going to happen. Just using a little bit of Newton knowledge, as you could call it, some really interesting predictions can be made about certain things. Here we have on the image two scenes here. I'm going to start with this one over here. These are soccer players or football players, they're probably rugby players actually, that are running around the patch here or the field, and they're surrounded in these plastic, you know, bags basically, so they can bounce into one another without hurting one another. So, what do you think they're just going to simply bounce off one another and it's not going to be a big deal? Let's see what happens here. Let's watch that again. It's pretty funny. The more times you watch it, actually, the funnier it is. This guy's feet actually go all the way up in the air. Okay, so this is actually an explainable phenomena just through Newton's third law. Let's see another example here. Here's a man, and a much smaller girl is going to run and try and jump into him, and you're going to see what's going to happen here. Yeah, yeah, it was almost too predictable. I can't believe she even tried. All right. So one of the things we need to understand to be able to kind of approach Newton's third law properly is the relationship between forces and interactions. So an interaction is between one thing and another. And in order for an interaction to occur, requires that a pair of forces acting on two objects occur simultaneously. So for example, when you put your hand on a wall, the wall's pushing on you and you're pushing on the wall. Remember, we were kind of talking about that uh, back in one of the earlier lectures when we were talking about normal force. You put a book down on a table, the normal force pushes back up, and that's what keeps the book from accelerating downwards, right? There has to be something accelerating it back to balance that force. So as long as you have that in place, you wind up with a net force of zero, and a net force of zero means nothing goes anywhere, and sometimes that's exactly what you want. Right, so here would be a pair of forces. This gentleman here is leaning up against the wall, and the wall is resisting him collapsing it. So there's a certain internal strength to the wall that is actually acting in the form of a force. So that creates what we call a force pair. You push on the wall pushes on you. So that leads us to Newton's third law of motion. And the way that he put it, this is translated from the Latin, of course, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. But it's more famously stated this way. For every action, there's an equal and opposite reaction. So just to demonstrate this, this is an image of a door as well as a wall over here that somebody just, in a fit of rage, punched the heck out of. It makes them feel better for whatever reason. And then, of course, right over here is an x-ray of somebody that punched the door, and there's actually a fracture right here in his hand. So obviously, not only was he punching the door, but the door was punching right back. Pretty foolish, actually. So Newton's third law of motion is can be dissected in the form of action forces and reaction forces. So the first force is called the action force. The other force is called the reaction force. And they are co-pairs of a single interaction, right? So one interaction has two forces, a co-pair. Okay? And neither force exists without the other, right? If you have a force that's occurring, then you get an equal and opposite force going in the exact opposite direction, which is what this says right here, are equal in strength and opposite in direction. And they always act on different objects. This is another important thing to note. So here we see looks like a man or soldier, probably in the Navy, firing an old school musket. As he fires the gun, his action actually is to move backwards. Or, I'm sorry, his reaction is to move backwards to the gun firing forward. Mathematically, it's real simple. It's much easier than F equals ma. It's a lot easier than even the Newton's first law, right, that we were talking about. And it's certainly easier than all of the linear motion equations we're talking about. It's just this. For every action, there's an equal and opposite reaction. For every force, there's an equal and opposite force right back, a copair. So FA is going to equal FB. Remember, these are both vectors. So here's a woman. She's pushing on a car. She has a very lazy boyfriend whom she should probably not be with. He's driving the car. So she's pushing, and her force is A, and the response that she's getting from that force is negative force B right back at her. So they're pushing with equal and opposite forces on one another. Simple rule to identify action and reaction. Sometimes these pairs can be a little difficult to put together, but let's just keep it, just to kind of help keep things in order in our mind, is that for an action, object A exerts a force on object B. So in this case, we're going to define object A as force A, right? Or I'm sorry, object A is going to exert force A. So that's the active or the action force. The reaction force is usually to be defined as object B, which exerts a force on object A. It's just right back at it. So a good example of this, and actually the classic example of this, is a rocket. So in this case, we see a rocket that's being launched from this military platform. This is a form of artillery rocket. This rocket, object A, exerts a force on gas. The gas is actually this material. It's burning. It's actually, there's a fuel in here. The fuel, as it's burning, is rapidly converted into a high energy gas. And that gas is object B. The reaction, and this is the reaction that we actually want, is that the gas, which is object B, exerts a force on the rocket, object A. And it's that force of the gas on the rocket that actually propels the rocket forward, right? It's not the fact that the rocket is putting a force on the gas. It's the opposite. The reaction is actually what we're looking for, at least in this design. Okay, so let's continue applying this to some other situations, right? So you say, okay, so the rocket, that makes sense, the gas. Okay, but what if they're solid objects? And so again, the classical example used for this is a cannon. So here I found a photograph of a large Byzantine cannon, and believe it or not, this cannon can still be fired. This is real steel shot or iron shot that could be loaded in, and this gun has in fact been fired in war. Anyway, this thing is huge, by the way. It was used for defending naval ports against battleships before the era of modern battleships. But it's been fired many, many times. Anyway, so when we fire this gun, right, this cannonball, as big as it is nowhere near as large as the cannon itself. So in this case, the mass for the cannon is very large. But for the cannonball, we want to be the acceleration very large, right? We want the cannonball to shoot out, but we don't want the cannon to shoot backwards. So that's the reason why you make a very large cannon. Okay, but notice in this case, F and F are both drawn to the same size because in fact, they're the same magnitude. So this is basically what the notes down here say. The same force exerted on a small mass produces a large acceleration, right? Small mass, large acceleration. Same force on a large mass produces a small acceleration. That's exactly what it says down here. That's not to say that there isn't going to be recoil in this situation, but the recoil hopefully will be small enough where the cannon will still be stable afterwards and they can reload another shot into it, fire it, without having to worry about the cannon rolling off on them. So one of the important things about Newton's third law of motion is defining the system, right? So we're talking about the cannon firing the cannonball, and before that, the rocket being launched into the air, fired by the gas, right? So here we see the force pairs reacting one with the other. So then that begs the question, at what point can I push on something and it moves, right? So let's talk about that. So let's consider a single enclosed orange. This is an orange out of the textbook that I like to use. Those of you that are using the textbook will see this image right out of it. Anyway, so here's an orange sitting in a cart, and this dashed area here around the cart is what we're defining as our system, okay? So any external force that is applied to the orange will accelerate in accord with Newton's second law. That's what this says right here, okay? we see here only the action force, which is the red vector. So this red vector, that if you were to pull on it or push on it or exert a force in this direction, as shown here, the entire cart is going to move, everything within this system. Now let's imagine in this case we have a anthropomorphized apple. Consider the apple and the orange and the apple pulling on it. Action and reaction do not cancel because they act on different objects. So what's happening here? How is it that the apple is actually able to pull on the orange? In this case, the apple should be able to pull on the orange, but you just said if for every action there's an equal and opposite reaction. Why is it that the apple is able to pull on the orange, but pull the orange along on the cart? Shouldn't they just be sitting there pulling on each other and going nowhere? That's an interesting question. And the reason why they don't cancel is because they're acting on different objects. So the external force by apple accelerates the orange. Think about this for a moment, right? This is conceptually a kind of a difficult concept. The apple's able to pull the orange right along, but the orange is also pulling right back on it. How is it that the apple's able to move it? Think about that for a little bit. So now let's redefine our system. Let's bring our apple and our orange, and this time we're going to configure it so that the apple and the orange are in the same system, right? This is kind of clever. By the way, we're going to come back to that earlier puzzle here in a minute. So think about that as we go through this. The apple is no longer external to the system, right? So in this case, the apple and the orange are in fact linked. But notice where we're putting our dashed lines, right here underneath the wheels and right underneath their feet. So the force pair is internal to the system, which doesn't cause acceleration. Okay? Action and reaction with the system cancel. With no external forces, there is no acceleration of the system. So the way that we're defining this is basically there's an apple and there's an orange, and they're pulling on each other, but they're not being affected by anything outside of this dashed line. And so they don't go anywhere, right? You can imagine that they're sitting on a frictionless surface, right? Because there's no external forces. They cannot put their feet on the ground and drag themselves across the ground. Of course, I'm giving you a hint towards the answer of the last puzzle that I gave you. But anyway, if you're pulling on something and you're standing on a frictionless surface, and they're pulling on something and they're standing on a frictionless surface, you don't go anywhere, right? Because there's no external force acting on you. So as you can see here, here's the same system, but with external force of friction on it. So friction between the apple's feet and the floor, right? So even though he's pulling and she's being pulled along, before they couldn't go anywhere, but now he is able to get traction. Doesn't really matter if she's able to get traction, and the male, presumably male apple, is pulling the female apple right along. I'm sorry, the orange. So I want to take some time to make sure that we nail vectors. This is a really important concept throughout physics, and as we're going forward in the class, you'll find that this symbol here, the F hat, as some people call it, or the vector symbol, is going to come up quite a bit. Vectors are very important in physics, and this is one of the reasons why people get afraid of it, because the math looks kind of ornamented. It looks kind of fancy, and it does look a little fancy, but it actually doesn't need to be that hard, right? So I want to make sure that we go through the vector components by the end of this lecture. So vector components. Vertical and horizontal components of a vector are perpendicular to each other. What does that mean? Well, perpendicular means at 90 degrees, right? So here's an arrow and here's an arrow, and they're at 90 degrees to one another. And so it turns out that a force, this force here, it begins here, and it's drawn to scale. Of course, we should always draw our forces to scale if possible. Would extend like this. And then we basically could draw one from this point, this tail here, to the beginning of the arrow, to that length of F. And we call that Fx. Why? Because F is in the X direction, on the X axis. And in this case, Fy goes up and down the Y axis. So these are the two components, right? Fx and Fy. So we can actually use that to determine different things, right? Sometimes we don't always need to know exactly what the full force is. That's, for example, a ball. If I throw a ball at a wall and I happen to hit it straight on, then I care what the force is here. But what if I throw the ball and it glances off the wall? Or it glances off of a window, and I want to make sure that a window is built strong enough to deal with glancing blows. Well, then maybe at that point I don't really need to worry about this. Maybe I need to worry about one of the components, right? So if I throw something like this, I might only care what the Fx component is of it. I might be getting a little theoretical on you. Don't worry about it too much. It'll make sense as we're going forward. But to work these things out, it's really very simple. It's just the Pythagorean theorem, the same thing we've been using since 4th grade, right? So remember, the Pythagorean theorem is that you take the square of the two legs, add them, and it equals the square of the hypotenuse of the triangle. And this is really what we have here is a triangle. Here's a leg, and here's the hypotenuse. So f squared is going to equal fx squared plus fy squared. That's what we have right here. This is just a restatement of the Pythagorean theorem. Okay? Or we could just take the square root of both sides and we actually get the resolution for the force, right? Force is equal to the square root of the sum of fx squared plus fy squared. Very, very, very rudimentary math. It looks kind of fancy because you got the arrows in here and you know, you can impress your friends with these little subscripts. But all it means is that you have a force with a y component and an x component. So let's start playing some kind of conceptual games with vectors, right? So here's Nellie Newton. And of course, Nellie Newton is a character out of my favorite physics book. So I like to use her. Nellie Newton pulls on the sled as shown. Which component of her force, F, is greater? And then the second question is, what two other forces not shown act on the sled? So which of the two? So there's two forces. There's an F of x, or I'm sorry, an Fx, and there's an Fy. Which of the two is larger? And of course, what two other forces that I have not shown, right? I've only shown her pulling on the sled, the tension on the rope of the sled. What two other forces not shown act on the sled? So why don't you take a quick moment. I'd pause the video right now and see what you can work out. Okay, so I've assumed that you've gone ahead and paused the video and that you've got an idea. And so let's show you the answer and see if you were right. So which component of her force is greater, and what two other forces act on the sled? Well, the first one should be pretty easy. My prediction is that it's going to be, well, I can look at, well, this one is shorter than Fx. So I'm going to say that Fx, which is the longer of the two arrows, is probably the right answer. And then what two other forces act on the sled? Well, I believe I already know the answer, but we'll see what you came up with here. So sure enough, I was right. The horizontal component Fx is greater. What two other forces not shown act on the sled? The weight, right? Mg. She's got an mg, the dog's got an mg, the sled's got an mg, even the rope, mg. Also the normal force, which keeps them from falling into the snow. You always got to keep in mind, weight and normal force are always going to be present unless you happen to be floating around in space. So let's do a quick practice problem. What is the resultant force on a box when two people push at 90-degree angles from one another? See diagram. So here's our box, and there's a force of somebody pushing at 300 newtons, which is a pretty good push, not heavy, but good enough. And here's another push coming from another direction. You'll notice they're 90 degrees to one another, so you can kind of see where this is already headed, right? That you got an Fx and an Fy. So person A pushes with 300 newtons of force and person B with 400 newtons of force. The other question that they want to know is, what is the resultant direction? Well, we already have a couple of tools to deal with this, right? We remember that we can solve this just using Pythagorean theorem. 300 squared plus 400 squared, add those two together, and then take the square root of it should give us the force, right? So let's let's go through that really quick. And here it is. I've actually done the calculation for you to make it really nice and easy. So here's the original equations. Force is equal to the square root of fx squared plus fy squared. This is just a plug and chug, right? Our fx is going to be equal to 300. Our fy is going to be equal to 400 newtons, right? Always make sure that you keep the units in there or else you'll get confused. So we plug those in. The next step is we get 90,000 newtons squared, right? Because not only does the newtons get squared, the number gets squared as well. So we get a newton squared unit, which is pretty strange. And then we get also over here 160,000 newtons squared. We sum them up to 250,000 newtons squared, take the square root of that, and we get a resultant force of 500 newtons. So we know that there's 500 newtons, but at this point we don't know the direction. Well, I kind of have already shown it down here. In this case, so all you do is you take the two vectors, tail to tail, this one and this one, and you'll notice I put them tail to tail. I put them like so, and then essentially I extend it out, dashed lines, just so I can keep track of where it was going in the F and in the Fx and the Fy directions. And the resultant force goes from tail here to this point up here where they match up. And so this is the direction it's going to go. The box is going to go up in this direction with a force of 500 newtons. So it's not 400 newtons plus 300 newtons because you almost would expect it to be 700 newtons. This is why vectors are so important, because the resultant vector might not have a force of 700 newtons where you could just add them together. Sometimes it gets a little more sophisticated. If you want to know the actual angle of this, you would need to know a little bit of trigonometry. In this case, I believe it's 53 degrees, but I'm not completely certain, which is say 53 degrees from Fx up this direction. But I'm not completely certain of that. That's just off the top of my head. Anyways, with that said, I hope that you kind of like that little problem. You can kind of see how two people pushing on a box can actually all be worked out using simple Newtonian physics. Not really anything hard here. This is just Pythagorean theorem. This is all that is. So let's do another one just to kind of solidify this. And this one might be pretty easy for you. So forces of 3 newtons and 4 newtons act at right angles on a block of mass 2 kilograms. Show that the acceleration of the block is 2.5 meters per second squared. That sounds like it might be a little challenging, but let's see if we can work that out. Well, obviously, if they're at right angles, we know we're using Pythagorean theorem again right away. So let's go ahead and open up our chalkboard program and work through this. Cool, let's see if we can have some fun with this problem. We've got two forces. We'll just say the first one, F1, is equal to 3.0 newtons. F2 is equal to 4.0 newtons. And they're at right angles. Okay, what does that mean? That means we have a force going like this, and we'll call that F1, and we have a force that's coming like this. We'll call it one F2. All right, so we already have the formula for it. Force equals square root, hopefully I got enough room under here, 3 newtons squared, looks like not, plus 4 newtons squared. Let's just start doing the arithmetic. It's actually pretty straightforward. It's going to be 9 newtons squared plus 16 newtons squared. F is going to basically equal, hopefully you can see this is going to turn into 9 plus 16, that's 25. 25 newtons squared, the square root of 25 is 5. So force is actually reduces, I'm just going to skip that step. 5 newtons, right? Because 9 plus 16 is 25, and the square root of 25 is 5. So that's where I get this from. So the resultant force is going to be presumably coming off in this direction. Just eyeballing it, right? Because if you put these end to end, it has to go in that direction. So this is F. So the real question is, we now know that F equals 5.0 newtons. All right. But the question says, verify that the acceleration on that object is going to be 2.5 meters per second squared. All right. We're just going to go ahead and combine Newton's third and second laws. All right. So this would just be simple F equals ma. What we don't know is A. We know mass, because mass, it tells us right in the problem, is equal to 2 kilograms. Clean up that M. And the force we know too, because we just solved that. So force is 5 newtons times 2 kilograms, all times acceleration, which is what we're trying to solve for. And then we basically take 5 newtons divided by 2 kilograms. Remember that newtons, I'll write it over here, newtons equals kilogram meters divided by seconds squared. So if we know that, then we can understand that we can go ahead and do this division, no problem. 5 divided by 2 is 2.5. 2.5, because kilograms here, they divide out here. That leaves us with meters per second squared. And look, it works. So we have verified that that will be the acceleration, 2.5 meters per second squared. That's a pretty good acceleration, by the way. All right, so let's go back. Cool. I hope you enjoyed that little thing there. The calculation is pretty straightforward. We just had to combine Newton's third law with Newton's second law. Falls right out for us. All right, so we have a couple of useful equations. You'll notice I spent more time emphasizing this because this is so easy mathematically as to be almost laughable. However, the concept can be really hard to put together. For example, a lot of you have not even thought about it. A lot of this is counterintuitive, but when you walk across the floor, you're applying a force, but that force is actually backwards, right? You're actually pushing back. And why are you being propelled forward then? It's because the floor actually exerts a negative reaction force on your foot that propels your body forward. Isn't that interesting? That you're not actually pushing yourself forward, the floor is pushing you forward in response to your pushing against it. I think that is absolutely fascinating. And you can think about that, right? If you were on a surface that didn't have the ability to exert that force back, for example, you were walking on water or you're walking on a frictionless surface, no matter how much you tried to walk, if it wasn't pushing back on you, you're not going anywhere, right? So your action is just to try to generate a reaction of forcing you forward. Fascinating, but a lot of people don't think about that. We think that frequently we think it's all in our own domain. All right, well, I hope this was informative and I hope you liked it. The next lecture is on momentum, and that is extremely cool, and it builds on these concepts in the third law. Take care. See you next time.